Hi, everyone. So then this is a very quick video, as it's just introducing yet another generalization of a fact you already know. You guys remember the rank and nullity theorem? The rank of a matrix plus the nullity of a matrix is equal to the number of columns of that matrix, n. So there's a generalization of that because of the theorem I just gave you. So it says then if you take any subspace of Rn, then the dimension of the subspace plus the dimension of its orthogonal complement is also n. This is the rank nullity theorem is a direct consequence of this guy. If you just say W is the row space, then W perp is the null space of A. So it literally says the dimension of the row space of A, rank of A, plus the dimension of the null space of A, the nullity, is equal to n. So it's just the rank nullity theorem in a more general sense. If you want to not watch the proof, you don't have to. Just remember this fact. It's kind of nice to remember. It does have some really, really great consequences. One is that it means then that the row space plus the null space, that if you take every single vector in Rn, it can be written as a sum of one from the row space and one from the null space. And the same can be said for the Rm space. When you look at the column space of A and the null space of A transpose, every vector in Rm can be written uniquely as a vector in the column space of A plus the null space of A transpose. Okay, so then assuming you're still here because you want to see the proof, I'll do it quickly. It's only one slide. Suppose that B and B perp are respectively orthogonal bases for the subspaces W and W perp. Okay, but that means we put them together, it has to be an orthogonal set because B is an orthogonal set, B perp is an orthogonal set, but since W and W perp are orthogonal to each other, all these vectors have to be orthogonal to each other also. So overall, it's an orthogonal set. That means that B union B perp, this set of vectors, has to be orthogonal and therefore linearly independent. I'm going to prove to you it's actually basis for Rn. So why take any vector in Rn now? The projection theorem just guarantees that there will be a vector, and it's unique, in W and one in W perp, so that V is the sum of those two vectors. But if W, that vector, is in the subspace W, then it must be a linear combination of its basis vectors, W of B. But since W perp is in the subspace W perp, it must be a linear combination of the vectors from B perp. But V is a sum of these linear combinations. So V is equal to a linear combination of vectors from B and B perp. Therefore, V is in the span of those two things. So V is in the span of the union of B and B perp. But that means then that everything, because I started that V is just some random vector. If V can just be any old damn vector, that means then that the span of these two sets, when you put them together, has to be at least Rn. And it can't be more. So it must be equal to it. So the span of the union of these sets of vectors spans all of Rn. And the vectors are linearly independent. That means they're a basis. So the union of these separate bases is actually a basis for all of Rn. Neat, right? Neat, right? So then by getting a basis for W and getting a basis for W perp, by putting them together, automatically it's a basis for all of Rn. But then if it's a base of Rn, we know that there has to be n of them. That's the dimension theorem I gave before. So the sum of the vectors here has to equal n. So therefore, the dimension of W, the number of vectors in B, plus the dimension of W perp, the number of vectors in B perp, that has to equal n because we now know there has to be n vectors. And that's it. That's the proof of that particular theorem. And that's enough for that video.